Hello, welcome to the course Excelling with Mathematical Modeling. Today we will be talking about models with varying gravity. So to start with, we look into Newton's law of universal gravitation, which says that every particle in our universe attracts every other particle with a force which is directly proportional to the product of their masses and is inversely proportional to the square of the distance between them. If you want to write them mathematically, then that force varies as the product of the masses directly and inversely to the square of the distance between them. And we get the formula. This is capital G m by r square, where this capital G is called the universal gravitational constant. Universal gravitational constant. We defined another term which is called E. It is called gravitational field strength, which is defined by F divided by m. So, but this m is the mass of the smaller object. If I want to see the unit of this, so force is calculated, the unit is Newton and mass is kg. Also, Newton is nothing but kg meter per second square, and this is divided by kg. This and this cancels, and you are getting meter per second square. So, if you note carefully, this is just the unit for acceleration. In this case, acceleration due to gravity. So, basically your gravitational field strength have a unit of the acceleration due to gravity. Now, near the Earth's surface, the gravitational force is m into g. So, this g is equal to F by m, which can be put as E, and F by m is equal to g m by r square. So, your gravitational force near the Earth's surface g varies as 1 by r square. So, the point of proving this is that in the Earth's surface, if a body is attracted, then the gravity varies as 1 by the distance square, which we call the inverse square law. However, when you are inside the Earth's surface, let us see what happens. So, inside the Earth's surface, suppose somebody is here, then this is the attracting mass. So, suppose you are moving from here towards the surface of the Earth. So, as you rise from Earth's surface, the effective mass of Earth's attraction also increases. So, it means that from here, if you now take a new g, that is equal to g by r square multiplied by m, where this m now increases as you move towards the surface of the earth. This r is now the distance from the center to this current location. So, if your aim increases, then I know that mass equal to density into volume. So, 4 by 3 pi r cube, that is the volume, multiplied by its density gives you the mass, and this r square and this r cube cancels. So, you get 4 by 3 pi rho g multiplied by r. So, inside the earth's surface, your nu g dash varies as r linearly. So, the take home message is that inside the earth's surface, if a body moves away from the center, it varies linearly as the distance, and on the surface and above, it follows the inverse square law, which varies as 1 by r square. With this information, let us take a example. So, it says that the acceleration due to gravity varies inversely as the square of the distance from the center when the attracted particle is outside the surface, and inside the earth the acceleration at any point varies at its distance from the center of the earth, the one which we just proved before. Let a be the radius of the earth and g be the acceleration on the surface of the earth. So, if we draw a figure, so let us see that this is the earth and its surface. Suppose A is a position of the particle and it is falling. So, this is the center of the earth, this distance is b and the radius of the earth is a. Let p be the position of the particle at any time t. So, a particle of mass m falls from the point A towards the surface of the earth. So, now the equation of motion will be so it is falling in this direction, it is attracted towards the center O. So, the force is attractive. So, the acceleration, that is the d2x dt square multiplied by m gives you the force, and the right hand side it is some mu 1 by x square multiplied by mass with a negative sign because force is attractive. So, this is our equation of motion, and now we have to solve this, say to find the velocity on the surface. So, what we are going to do is we want to find the velocity from the point A on the surface and at the center, and let us see how this varying gravity affect this model. So, you cancel this m from both sides and you get your equation d2x dt square is equal to minus mu 1 by x square. Now, to solve this kind of differential equation, you have to multiply both sides by dx dt, d2x dt square minus mu 1 by x square into 2 times dx dt. This gives ddt of dx dt whole square, which is equal to 2 mu 1 by x square dx dt. Now, this will give d of dx dt whole square is equal to minus 2 mu 1 by x square dx. You integrate both sides, this gives dx dt whole square, this gives 2 mu 1 by x plus some constant. Now, you have to find the value of this constant. So, if you notice that initially the particle is at the point A and it is falling freely from that point. So, the initial velocity is 0 and the distance this much is b from the center of the earth. So, at the point A the velocity is 0 and the distance is b. So, this information we put here, that at time t equal to 0, your dx dt is also equal to 0 and your x is equal to p. If you substitute it here, you get 0 is equal to 2 mu 1 by b plus constant, which implies constant equal to minus 2 mu 1 by b. Now, you substitute this here and we get dx dt whole square, which is equal to 2 mu 1 1 by x minus 1 by p. Now, on the surface the acceleration due to gravity is g and it follows the law mu 1 by x square, and at the surface this value is a, I mean the distance is a. So, I can write g is equal to mu 1 divided by a square. So, what we are doing here is we are trying to find out the value of this constant of proportionality mu 1 in terms of the gravitational constant. So, we say that on this surface of the earth the gravitational constant is g and also it follows the inverse square law. So, it is mu 1 by a square and on the surface the value of x is a. So, this has to be equal and this will give us mu 1 equal to g times a square. So, you substitute here and you get 2 g a square 1 by x minus 1 by p. Now, if I want to find what is the velocity of this particle on this surface, then I say that if v1, this is the velocity of the particle on reaching the surface, then I get dx dt equal to v1 and x is equal to a, because x is measured from the center O and here this value of x is equal to a. So, I substitute it here and I get v1 square equal to 2 g a square 1 by a minus 1 by b. Can simplify this a little, 2 g I put 1 a inside. So, it is 1 minus a by b. So, I can say the velocity is given as the on the surface v1 is equal to square root of 2 g a 1 minus a by b. Though I put a positive sign here, but since it is falling in this direction and x is measured from this point, the value of x decreases with time and hence actually the velocity should be taken as a negative quantity. Now, if somebody asks, okay, what will be the velocity at the of the particle when it reaches the center O? Let us see how your equation of motion changes. So, there is the two part of the problem. The first part is that it is falling from the point A till it reaches the surface and then from A again it goes to O. The reason for doing this is that in this particular space you have an inverse square law and in this the force varies as the linearly as the distance. So, if we consider the second part, that inside the earth, so your equation of motion inside the earth, this is going to be now m d2x dt square is equal to minus m some mu 2 x. So, with the same logic that it is an attractive force, and hence this negative sign, the mass cancels from both sides and you multiply by 2 dx dt on both sides, 2 times dx dt. So, this will give d dt of dx dt whole square is equal to minus 2 mu x dx dt. So, if we integrate, d of dx dt whole square is equal to minus 2 mu integration x dx. So, if you integrate d of anything, it gives you that thing back. So, dx dt whole square is equal to, sorry, this is mu 2 minus 2 mu 2 x square by 2 plus constant. Now, before finding the constant, let me find the value of mu 2. So, with the same logic, on this particular surface, if we consider now the motion in the downward direction, that is inside the earth, it follows linearly. So, basically if I follow this on the surface, mu 2 a must be equal to g. So, this one was considered for this lower part and the previous one was considered for this upper part, but on the surface the value of g remains constant. So, which is equal to, for if I consider from the lower point of view, this g is also equal to mu 2 a, because it follows the linear law. So, from here you can get mu 2 equal to g by a. So, this you can substitute here and you get dx dt whole square is equal to minus g by a x square plus constant. Now, I have to use the initial condition to find this value of the constant, and the initial condition is at time. So, it is something like it has fallen from this. So, at this point, what are the information available? So, here I need the velocity and the distance. So, when x is equal to a, what is the value of the velocity? And that we have already calculated, that is 2 g a 1 minus a by b with a negative sign. So, this is exactly what we have calculated here. So, on the surface what will be the velocity, and which has followed the inverse square law. So, to calculate the velocity of the particle when it reaches the point O, our initial velocity we have taken that what will be on the surface. So, we substitute it here and we get 2 g a 1 minus a by b equal to minus g by a square plus constant, which implies our constant is equal to 2 g a minus 2 g a square by b plus g a. So, 3 g a minus 2 g a square by b. If you simplify a little, so I can take a g common. So, 3 minus 2 a by b. So, I substitute the value of constant here in here, and I get the equation as dx dt whole square is equal to minus g by a x square plus 3 minus 2a by b multiplied by h. Now, the question is, what is the velocity of this particle once it reaches the center O? So, when it reaches the center O, your x becomes 0, because x is calculated from here. This distance was b, this distance was the radius of the earth A, and p be the position of the particle at any time t, and such that this OP is equal to x. So, you just substitute x equal to 0 and you get your dx dt square, which you name as say v2 square is equal to ag 3 minus 2a by p. So, at the center your velocity is going to be square root of ag 3 minus 2a by p. We now look into the numerical solution of this varying gravity model. So, as you can see, this is the actual equation, and we write this second order differential equation as a system of two first order differential equations. So, what we do is we substitute dx dt equal to y, and if I differentiate dy dt, I will get d2x dt square, and hence dy dt is equal to minus g x square a square by x square. Now, g is the acceleration due to gravity. So, we take the value of g to be 10. The radius of the earth is approximately 6400 kilometer. We scaled it and we take the value 6.4, and the value of h is 0.1. So, what we are going to do here is to check using Microsoft Excel that our numerical solution also matches with the analytical solution. Now, we know that at time t equal to 0, we have taken that the value of the velocity x dot is equal to 0, and x is equal to some b, the value of which we take as 10, and the value of the radius is a, which is 6.4. So, if we calculate the velocity, this will be given by minus square root of 2ga 1 minus a by b. Now, this will be equal to, if I substitute all the values, 2 times 10 into 6.4 and 1 minus 6.4 divided by 10. If you calculate this value, you will get approximately 6.79. Now, we solve this set of differential equation, and we will see that it is approximately matching with this value. So, let us use Microsoft Excel. So, as you can see, I already have time from 0 to 15. The value of the acceleration due to gravity is 10, the radius is 6.4, the value of b is 10. So, that is why initial value is 10 at time t equal to 0, and dy dt is nothing but x dot, that value is also 0. So, let us now calculate this. So, this is equal to this x plus h, which is a constant. So, I put a dollar multiplied by the y, which is this value, and the value of y is equal to y0 plus h, which is a constant, multiplied by the value of g, which is 10, again a constant multiplied by a square, which is again a constant. So, I put dollar divided by x square. So, this 10 square, and this is in a bracket. So, h, and this is with a negative sign. So, let us now drag and calculate the values. So, if we now plot them, this is what we get. Go to insert, go to the chart and click this. So, this will give the curve. So, the series 1 is the x values and the series 2 is the y values. So, y gives you the velocity and x gives you the distance. Now, if you look into the velocity value, you can see that in this step it has attained the velocity as minus 6.72, which is approximately equal to this, and the distance is 6.5. So, basically when the radius is, or when the x value is approximately equal to 6.4, here it is 6.5, and your velocity is approaching 6.79, here it is 6.72, some sort of approximate value which is approaching as the particle reaches the surface of the earth. So, thus we verify that our analytical solution is same as when we put the numerical values. So, summing up, we took a model with varying acceleration, we solved the equation analytically, and we got a relation between the velocity and the distance, and then we use the numerical solution using Microsoft Excel, and we have shown that that matches with our analytical calculation. So, in our next lecture, I will be talking about various kind of tumor growth models, namely say the linear growth, the exponential growth, the logistic growth, the Gompertzian growth, and many more. So, the reason we are studying so many growth model is that this tumor vary from person to person, and we really do not know which model will actually fit to a particular kind of tumor. So, we will be going through all these growth models and learn their dynamics. Till then, bye bye.